In this video, we'll explore ozonolysis, a powerful reaction used to cleave carbon-carbon double bonds. This two-stage process breaks the pi bond and the sigma bond, resulting in the formation of carbonyl compounds. Our goal is to predict the major products for the reaction of 2-methylbutyene with ozone in the first stage, followed by treatment with a reductive workup agent like dimethyl sulfide DMS in the second stage. Ozonolysis achieves a complete cleavage of the carbon-carbon double bond. We can predict our two major products simply by imagining replacing that double bond with two separate CO double bonds. First, let's look at the C2 position. This carbon atom has two alkyl groups attached. Breaking the bond here yields a ketone, specifically acetone, or propan-2-one, fitting the R2CO form. Second, the C3 position has one alkyl group and one hydrogen atom. When that bond breaks, we get an aldehyde, which in this case is acetaldehyde, or ethanol, fitting the RCHO form. We typically divide the ozonolysis sequence, a classic example of oxidative cleavage, into two conceptual stages: ozonide formation and workup. Stage 1. Ozonide formation, cycloaddition, and rearrangement. The reaction begins with ozone, a potent electrophile, reacting with the alkene. Step 1. Initial cycloaddition, 1,3, dipolar cycloaddition. The pi electrons of 2-methylbutyene attack one end of the ozone molecule, while the third oxygen atom simultaneously attacks the other carbon. This process is concerted, meaning it happens in a single step, without intermediates, and is known as a 1,3 dipolar cycloaddition. This forms a highly unstable, 5-membered ring intermediate called the Molozonide, a 1,2,3 trioxylane. Step 2. Molozonide rearrangement. Due to its instability, especially the presence of two adjacent OO single bonds, the Molozonide immediately fragments. It breaks down into two fragments: a carbonyl compound, the ketone or aldehyde product, and a reactive species called a carbonyl oxide, a civetarian. Step 3. Formation of ozonide, secondary cycloaddition. The two fragments, carbonyl and carbonyl oxide, quickly recombine in a second 1,3 dipolar cycloaddition, but in the opposite orientation. This rearrangement creates the more stable 5-membered ring called the Ozonide, a 1,2,4 trioxylane. Due to its instability and the fact that the ozonide is often shock-sensitive and potentially explosive, the reaction mixture is typically kept at very low temperatures. For example, at -78 degrees Celsius using dry ice, and is never isolated, moving immediately to the next stage. Stage 2. Reductive workup. The ozonide intermediate must be cleaved safely to yield the final, stable, carbonyl products. This is achieved by adding a reducing agent. Step 4. Reductive cleavage. The reaction mixture is treated with a reducing agent, such as dimethyl sulfide, or a mixture of zinc and acetic acid. This reducing agent facilitates the final cleavage of the ozonide, ultimately leading to the breaking of its OO bonds. In essence, the agent accepts an oxygen atom that originates from the ozonide. For example, when using dimethyl sulfide, it is oxidized to dimethyl sulfoxide, DMSO, while the ozonide structure is reduced to form the final carbonyl products. As a result, this cleavage process releases the final products we're looking for, specifically the fragment derived from the original alkene carbon that had two methyl groups, at position C2 of 2-methylbutyene, is released as a ketone. And the other fragment, which came from the original alkene carbon with one methyl group and one hydrogen atom, at position C3 of 2-methylbutyene, is released as an aldehyde. Now, let's compare this ozonolysis reaction with three other related cleavages that are important to remember. Reaction 1 involves 2-methylbutene treated with hot concentrated potassium permanganate, KMnO₄. Since this is a vigorous oxidative cleavage, the carbon-carbon double bond is broken completely, and any aldehyde product is further oxidized to a carboxylic acid. Reaction 2 uses 2-methylpropene with the same conditions. Here, the terminal carbon, a CH2 fragment, will be fully oxidized to carbon dioxide and water, while the other substituted carbon becomes a ketone. Reaction 3 is the oxidative ozonolysis of 2-methylbutene using hydrogen peroxide, H2O2, in the second step. This method also cleaves the double bond, but crucially, it converts the aldehyde fragment to a carboxylic acid instead of stopping at the aldehyde. And that brings us to the results of the reactions in this video. Make sure you compare and summarize them for your notes. Let's summarize. Step 1. Initial 1,3-dipolar cycloaddition of ozone to the alkene forms the highly unstable Molozonide. Step 2. The Molozonide rapidly rearranges by fragmenting into a carbonyl compound and a carbonyl oxide. Step 3. These fragments quickly recombine via a secondary 1,3-dipolar cycloaddition to form the more stable Ozonide. Step 4. Finally, reductive cleavage of the Ozonide using an agent like DMS yields the final aldehyde and ketone products. Let's organize by keywords. A concerted reaction where two molecules join to form a new 5-membered ring structure. The highly unstable primary intermediate formed by the initial cyclic addition of ozone to an alkene. A highly reactive species formed during the rapid breakdown of the Molozonide, which then quickly recombines to form the Ozonide. A workup procedure using reducing agents to safely convert the Ozonide into stable aldehydes and ketones. To wrap up, those who wish to deepen their understanding of ozonolysis and its applications are encouraged to study the following topics. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.